This section, we're going to talk about increasing, decreasing, and piecewise functions and applications. So the objectives here is to graph functions looking for intervals on which the function is increasing, decreasing, or constant. And we're going to also find the estimated relative maximum and minimum. We're going to have a given application. We're going to find the function that the models of the application. We're going to find the domain of the function and the function values, and then the graph of the function. Graph functions define piecewise. So these are our objectives. Here it says on a given interval, if the graph of a function rises from left to right, it is said to be increasing, which makes sense when we look at a graph. Let me draw it in a straight line. And my apologies. Let's see. Just determined not to draw a straight line. Okay, so I'm trying to draw a graph here so you can have an idea as to what I'm talking about. There we go. Now, we know that this is the y-axis, and we know it goes off to positive infinity here. And we know this is still the y-axis, and when we go downward, we're going to the negative infinities. When we look at this vertical or this horizontal line here, it's our x-axis. And we know in this direction here, we're going off to negative infinity. And in this direction here, we go off to positive, and it's still the x-axis. All right, so this is saying whenever we have some kind of function moving left to right, it's increasing. Well, that makes sense because we are moving in the positive directions, right? Now, if the graph drops, so say from left to right, it's dropping, we're moving into a negative section. So that is considered decreasing. If the function values stay the same, so basically, if this is what our function value looks like, right, it's consistent at a specific point. It's consistent at a specific point. Okay, so a function f is said to be increasing on an open interval, I in this example, if for all a and b in the interval where a is less than b implies that the function of a is less than the function of b. And here we go. We have our order pairs. So a is my first interval, and then f of a, which makes sense because whenever we talk about a function, we get some function name. In this case, we're calling it f of x. And my outcome yields y. So that makes sense as to if we're letting a represent x, then f of a, which is equal to y, is my y value in this coordinate. So they have these 2 points here, and they said this is f of a, and this is f of y, right? It's equal to y, or excuse me, f of b. My apologies, this is y. So we have those order pairs, and then we have our a and b, and we come up with these intervals. Now, if you notice, it is moving upward from left to right, this function is. So we do have an increasing function, and it's actually happening between these intervals. And if you notice, these intervals are open circled. So it is an open interval. If it's a closed circle, we call it a closed interval. A function f is said to be decreasing on an open interval I if for all a and b in this interval, a is less than b implies that f of a is greater than f of b. So which makes sense because here we are. We have our f of b and our f of a. And we have this function that's decreasing, right? It's dropping left to right, and it falls between these intervals. So this is called decreasing. A function f is said to be constant on an open interval I if for all a and b in the interval where f of a is equal to f of b. We get this straight line. It's constant. It's consistent, meaning that it's just not changing. It's staying the same, and it's at that one particular point. Suppose that f is a function for which f of c exists for some c in the domain of f. Then f of c is a relative maximum. If there exists an open interval I containing C such that f of c is greater than f of x for all in I, where c is, this messes me up right here. This is talking about, they called it that this interval is called I, and we have all x's in I, where it says x is not equal to c. So I'm fixing to show you that it'll make better sense when I start showing it to you. F of c is relatively minimum if there exists an open interval in I containing c such that f of c is less than f of x for all x in this I interval where x does not equal c. Okay, so let's talk about that here in just a minute, and it'll make better sense. Whenever we're looking at our functions on a graph, if you notice that we have this, right, we have this decreasing function from this point here to this point here, and it's decreasing. And then from this point to this point, right, from this point to this point, it's increasing. This was a decreasing. And then we get to this C2 to C3, it's decreasing again. And then we get from C3, it increases, right? Well, let's talk about what is my relative maximum and my relative minimum. Well, it's exactly the way it looks. Let me get my highlighter right quick. This right here is the bottom of this parabola, right? So this is going to be a relatively minimum value. It's a minimum. And then we have this peak up here at the top, right? And that's my relative max. And then we have another relative min. Okay. So a car distance application says two nurses, Kara and Mattis, drive away from a hospital at right angles to each other. Kara's speed is 35 miles per hour and Mattis is 40 miles per hour. So we're going to express the distance between the cars as a function of time of dt, where time is going to be my x value here. And we're going to find its domain. All right. So it says suppose that 1 hour goes by. At that time, Kara has traveled 35 miles. Mattis has traveled 40 miles. We can use the Pythagorean theorem because it did say, when you go back to this first one here, it said a right angles. So a right angle is literally got a 90 degrees angle. And a Pythagorean theorem means that we have a triangle with a right angle. Okay. To find the distance between these, the distance would be the length of the hypotenuse of a right triangle, the legs measuring 35 miles and 40 miles. After 2 hours, this triangle legs would measure 70, which makes sense, 70 miles and 80 miles, right? Because they said that 35 mile and the 40 mile was in 1 hour. Well, if I double that, we get the 70 and 80. Noting that the distance will always be changing, we make a drawing. So if you make a drawing, it'd be easier sometimes. And let t equal time in hours. And Kara and Maddie have been driving since they left the hospital. So here is a diagram of it, and it makes a great picture. So what we know is, we know, let me get my highlighter again. We know this leg, right? This one is Mattis's driving from the hospital. And this is Kara's leaving the hospital. But we don't know what the hypotenuse is. So if we use the Pythagorean theorem, right, which we know is a squared plus b squared is equal to c squared. C squared is the longest leg of the right triangle, where a plus b should add up. If it doesn't add up, to equal C. A squared plus B squared, again, should add up to equal C squared. If that doesn't happen, then we know something went wrong, or it's not a right triangle. I mean, you could have got it right, but it's just not a right triangle. So let's do this. So we have D of T, and we're going to square it. And that's going to equal, you can call M for Mattis squared plus K for Kara squared. And let's plug in what we know. We know that Mattis is 40 feet. And they're plugging in T for time. So that's a notation. I just wanted to show you in a minute. And when I do that, now let's go ahead and let's get an answer here. So I got 40 squared plus 35 squared. Oops. I gotta type in the square. Okay, I get 2,825. So let's keep on going. So when we did that, they said, well, we could plug it in our distance formula, right? Which makes sense, because let's go back here. Our Pythagorean theorem is this right here. So if I do that, what they've done is they square rooted both sides to undo the square on the D of T. And that ends up looking like our distance formula. Pretty close, because our distance formula, for those of you that needs a refresher, is when we got two order pairs and we're finding the difference between the two order pairs. In this case here, we're not finding, the distance between two order pairs. We're just finding the distance of the time it took between the driving. Does that make sense? Okay, so now that we've done that, we square rooted both sides, right? To undo the square on the T of, or D of T. Put it in the calculator, get the square root of 2,825. They went ahead and put the T on both. And when you do that, you got the T squared. So we would have had the two, well, actually, let's not skip the step so you can see where it came about. So we would have had what, 35 squared, which would have gave us 1,225 T squared plus, because you would square everything inside that parentheses. And then you would have got the 40 squared, 1,600 T squared. And then, of course, we have, it should come out as 2T squared. So that's a notation error there. So that's why I don't really want to plug in the T until the end. So if you have that error, just know you don't have to plug it in right then. Just know that we are talking about time T, and we're going to plug it in at the end. All right. So I'll take the square root of the 2,825, and I get 5 square root of 113. And we want an approximation. We're going to round to the nearest hundreds. So I'm going to get it in decimal form. When I get it in decimal form, I get T is approximately 53.15. Now, if they wanted to talk about seconds or whatever minutes, you would plug it in there. Okay, so now that we're talking about the time travel, T must be non-negative. The domain is the set of non-negative real numbers, which makes sense because we want to know time, and whenever we want to know time, we want to know the positive value of it, right? So the domain of it, again, would be 0 up to positive infinity. I put a bracket on 0 because we're going to stop on 0 because you can include 0 on time. I put a parenthesis on infinity because I cannot stop at infinity. All right, so now let's talk about piecewise functions. I'm using a different output formulas for different parts of the domain. So we have these functions here that's given to you. You got three functions. We got f of x is equal to x plus 1 equal to 5 and x squared. And it said for each one of these, we have some kind of restrictions, right? It says that when x plus 1, we get where x is less than negative 2. When f of x equals 5, then we say we have x falling between negative 2 and 3, and it can include them. And then when we have f of x equal to x squared, it says x is greater than 3. So now what we're going to do is we're going to figure out, we're going to find these particular points, right? So whenever we look at this, we're going to plug in for x, right? We're going to plug in some values. In fact, you can use a graphing calculator. It is going to be phenomenal at helping you find these points, but I do like for you to be able to calculate it. All right, so for this first one here, I got x plus 1. We plugged in negative 5, and it gave me, and the reason why, let me stop for a second. The reason why they picked negative 5 and negative 3 is because it said x is less than negative 2. And if you go to the number line, we got 0 here. We got 1, 2, dot, 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 infinity, negative 1, negative 2, dot, 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 negative infinity. So all values that I would plug into this first one needs to be less than negative 2 because it said x is less than that. If that's so, then we got negative 3, negative 4, negative 5, and so on. So they picked negative 5 and negative 3, so let's plug it in. When you plug in negative 5 for x, we get negative 4. When you plug in negative 3 for x, we get negative 2. So we got these values here. When we go plot them on the graph, we know that this particular function will have something going on with the order pairs of negative 5, negative 4, and order pairs of negative 3, negative 2. So that's good to know for the first function. When you take this last function here, well, there's no x variable on this 5, right? Where you saw on the first one, it had x plus 1. So we know no matter what I plug in for x, my y is constant at 5. So we'd have this order pair 0, 5. So 0 is a good point to pick because if you look, it will fall between negative 2 and 3. So, and it was an easy point to work with. Now let's look at, and let's plug another point. They said, well, since it can equal 3, let's plug in 3. Still get an order pair of 3, 5 because y is not changing in this one. And then we could say, what about 4? Well, 4 exceeded it, so we wouldn't want to use that. Oh, we're looking at x squared now. Okay. X squared says that we have where x is greater than 3. So basically for the x squared one, we're going to pick all points on this side of 3, which yields out to positive infinity. So they picked out 4. And when they picked out 4, so now I got x. Let's plug in 4 for x. We got 4 squared for x, and it gave me 16. So that order pair would be 3. Oops. Let me erase this. Would be 4, 16. There we go. All right. Now it's telling us whatever points we pick for x, it's got to be bigger than 3. So we could pick 10 if we wanted to, plug it in. And what do we get? 10 squared is 100. So that should have been 10 squared. That was a typo there. So when you come plot the graphs, and we'll get a new one, you could plot that one too on the unit circle and look at the difference between them. So we got another piecewise function here, and it says 1/3 x plus 3. It could also be written like this if you wanted to, just whatever works for you. It said x is less than 3. So if 3 is here and it's less than, see, and there's no equal sign, so we're not going to include 3. So I'm going to pick all points to the left of 3. When I pick all points, you can pick 2, you can pick -1, you pick 0. 0 is a good one to pick. If I pick 0, if I plug in 0 for x here, I'm going to get 0 plus 3, because 1/3, let me write it out. 1/3 times 0 is 0, plus 3 is just 3, so that order pair is 0, 3. So we're going to plug in 0, 3 right here. And then, and it's an open circle because it's not equal to, and it approached 3, look. So you see here, it's open at 3. That's what happened right there. Then you just plug in other points, and you put an arrow on the end because it's still constantly going. So we know we have an increasing function here, and it's going to be from negative infinity to 3, and I'm going to put a parentheses on the 3 because it's not equal to. However, this next one here says x is greater than 3 and or equal to 3. So it has a solid circle here at 3. And then I'm going to pick points on this side of 3, onto the right side of it. They're bigger, so I can pick 4. Well, that gives me -4, right? Because it's just negative x. So that order pair would be 4, -4. I can plug in 5 and so on. And what's happening is I have a decreasing function here. And that interval is going to be 3. Oh, it's going to be a bracket because 3 is included off to negative infinity. Oops, you should always write the smaller number first. Okay. All right. So we have another piecewise function here. And as we notice, this first one says x cannot equal -2, right? So if it cannot equal -2, then whatever happens with that function at that specific point, it's not equaling it, right? So how do we get that? How do we know it can't equal -2? Well, because we got a fraction here. And in a fraction, you cannot have 0 in the denominator. If I have 0 in the denominator, then I have an undefined fraction. So if you plugged in -2 for x, right, you get -2 plus 2, and that gives me 0. So that right there is where that restriction came from. And then you can plot in points for x to figure out what y is. This next one here says we have f of x is equal to 3. All right, so y is not changing, but x is. X is changing all over the place. Well, that means I need to plot wherever I see, and I pointed at the wrong one at the first, guys. This one is for the second value here. This one here, as you can see, it's an open circle at -2 because you can't equal it, is correct. And you plug in x values to figure out these other points on this line, and it is an increasing function. On this other one, though, it's consistent because y is not changing. So everywhere as I plug in for y equals 3, these are what I get. You can draw a straight line, or you could just say it happens just at that point. But x is constantly changing. All right. The next one is talking about the greatest integer less than or equal to x. The greater integer function pairs the input with the greatest integer less than or equal to the input. So you think about it, if you plug in -4, the greatest is -4. You would round this one. So this is just showing you some shortcuts. If you like this, I say review it. If not, I would just stick with what the other. Thank you.